Hello everyone, we're live, March the 9th. Alright, let's do it. Let's see what we have today. But before we go into it, first of all, log into this. I think somebody must have responded. Take a look. Yeah, let's take a look. What did they say? When you think about the array, you think the array's length is predefined and it cannot be changed. I'm mainly a Python programmer, so that I do not pay much attention to the array size. Say if we think the array is a Python array whose length can be adjusted, the linked list solution will be very similar to that. It's not really about the array size, but it's still how should I say? Array size. Length can be adjusted. I mean, when you adjust, is Python array implemented as a linked list? No, it's not. Python array is still an array. It's a list. You delete anything in the list, it's still going to cause ON. I mean, the removal will be different. I mean, the insertion and removal, they'll all be different. You can insert at the end, that's fine. You can also insert at the beginning. You can insert at the beginning, insert at the end. I mean, the only thing that is the difference is I think the major difference is in how removal is handled. A linked list, but you still have to traverse. You can argue that in linked lists you have to traverse and then delete. In this you have to, but you still have to. Isn't delete Python list? Delete runtime. I think it's still ON, right? Okay, take a look. Oh, we hit 1,000. Probably still the same answer. Yeah, it's the same answer. I was hoping that they can add more, but it's the same answer. Oh, we hit 1,000. All right. No, we just want to know delete contiguous vectors. O1 to index the vector with proportional over allocation. Range is that's a different. So we probably just have to go back to here. About the complexity. Yeah, set removal is average to 01. Yeah, list. Oh. Oh, okay. Have a list. Oh, I never know about this. Copy, append, pop, insert, average case, amortize the worst case. Get, set, delete. Yeah, delete item is ON. So find it is ON and delete is also ON. Okay, so I think I can answer. A linked list can remove an O1, but then you say now I think it's still worth continue this discussion. I mean, I don't think he got what we meant. Yeah, I mean, you can adjust the length, that's fine, but adjusting the length will cost you. What's the difference? You can remove a node, an array. We either remove an element, an on, or use a flag, or use a flag. Which will incur more memory usage. Other than that, the rest are pretty similar. The rest are pretty similar. Pretty similar between the linked list and array implementation. I may insert, yeah, we can always insert at the end. Or, yeah, we can insert at the end. We can just traverse, not fine, we can insert at the end. So it's fine, it's fine. Or insert the head, doesn't really matter. Alright, I think this is going to be my last response to this. This is dragging on a little bit too long than I want. Anyway, let's go to today, see what we have today. It's tree, I like trees. Add one row to the tree, ooh. Any place? Given a root, okay. Add a row of nodes with value v to the same value at a given depth. Okay. Okay, that's fine. So give a depth. So you need to go to the depth and then add it. Adding rule is given a positive integer depth for each not no tree. So no, we don't deal with it. In depth d minus 1, create two tree nodes with value v as ends in left and right, and then and the original left subtree should be the left subtree of the new left subtree root, and its original right subtree should be the right subtree of the new right subtree root. Okay, that's fine. If depth d is 1, that means there's no depth d minus o. Then create a tree node with value v as the new root of the whole original tree. And the original tree is the new root's left subtree. Okay, so we want to, there's a boundary tree. So we're gonna, value is 1, depth is 2. So 1, 2. So we're gonna add at level 2. So we have the original subtree is this. So we add 1, 1, and this is going to be the left, and this is going to be the right, okay? And this one, 1, 3, 1, 2, 3, so we just add at the bottom. Wait, no, not at the bottom, we change this, so this level, so we change the whole level into our value, 1, 1, and then we push this, okay? That's good. That's it, no more. They give a boundary tree at least one tree node, so they won't give you an empty tree. Okay, let me think. Doesn't seem to be very complicated, but it might require some ingenious if we want to use recursion to do this, or maybe not. So we're gonna find, so to find the depth, that's easy enough. We just we can use DFS, find the depth, right? So left and right, and then we just keep counting the depth. And once the depth is found, like this node, we know this node is depth 2, right? This is depth 1, this is depth 2. So we find the depth, we find the node, then this node, we need to also know if it's a left or a right, right? So we need to have a flag to say it's a left or right. And when we hit there, and we know it's a left, then we can just change the value? Yes. Hold on. We need to create a new node, right? We need to create a new node. So we're going to create a new node. So for the parent, it doesn't care. It just go here and here. But if it's the d-1, then we care, right? So if the d-1, what we're going to do is we're going to create new one. So that's actually is at this level, right? That's this level, d-1 level. Then it's a left and a right child is going to be our new nodes. What if we only have one child originally? It doesn't matter. Yeah, it doesn't matter. So this one we're gonna create two nodes, right? Two nodes, and we'll create two nodes, a left and a right. And then for the left, we're just gonna say this left equals new one, and new one's left equals this one, and that's it. And we can just return right there. Yeah, I think that's pretty much it. And for here, we just go. I mean, we'll go to all of the branches, right? All the branches, and then in one of the branches we hit the depth. Here, actually, we hit the depth. That's 3, 1, 2, 3. So it's the 3. So it's 2 that we hit at 2, and then we create 2 ones, and on the left. That's good. What about the case of the root? If we want depth as 1, which means we want 0, but we go in and there's no 0, right? There's no 0. That's a special case. What we're gonna do is just create one and then assign it to the left. I think we have an idea. It's actually simpler than I had expected. If our idea is correct. So far, not so sure, but we are going to try. Okay, so we're going to copy all this. Yeah, we're going to do it in DFS because it's easier to handle each individual node that we encounter. BFS, I mean, anything you can do with DFS, you can do with BFS. But I feel like DFS is easier. So for V, you have D. Edge case first. If D equals 1, then we're gonna do. What are we gonna do? We're gonna do new root. New root equals tree node. Okay, just return directly. I'm gonna return tree node. Val is V. Left is root, and that's it. That's the edge case. Now, after the edge case, we have DFS. We need a node, which is a tree node, and we need a level. Yeah, level, that's an int. And we're gonna return, actually I'm gonna return nothing. We don't have to return anything. So in this case, I'm gonna say if level equals d-1. We're gonna do a bunch of stuff. Let's say pass. Else, if level is not equal to d, minus 1. How do we end? We find it, then we can just end it, right? So elif, right? Elif level is smaller than d minus 1, right? If it's smaller, then we need to go dfs node.left level plus 1, dfs node.right level plus 1. So we need to go deeper, and if it's larger, then we end. That's good. That's good. And we also we can do it also here if node, right? If node, then we check these. If not node, we don't check. Okay, now we're at there, so we're gonna say I'm gonna say node dot left equals a new tree node whose value is v and whose left equals node dot left, and node dot right equals a tree node value is v and right equals node dot right. And that's it. We're gonna call dfs root. Now, our first level is going to be 1. That's our initial level, which means if we do 2, level 2, then that's what the first one that we can handle. And after we handle it, it's end. And we're gonna return root. Do you want to return anything here? I don't need to return anything. Yeah, I don't need to return anything. Okay, so let's give this one a shot. I'm gonna put this inside and just run the test case and see if it passes. Okay, and this one pass. And how about this one? This one will be, I'll actually just do it here. So 1, 2, let's just say 1, level 3, 1, 2, 3. Let's see, okay, pass, good. And the last one, we're gonna try a level 0. No, that's 1. Level, not level 0, level 1. If it's level 1, we're just gonna add something in the front. And how about we do 1, 2? Oh, we already did. I think 3 we already did. What if we do 4? What's gonna happen? Is this gonna be error, like test case error? No, we can do actually 4. We can do 4. Maximum depth of the given tree. Yeah, we can do 4. Maximum depth of the given tree plus 1. Maximum depth is 3, so 4 is possible, right? So it's just gonna be a, yeah, but 5, yeah, 5 is not gonna be possible. So let's submit it and see if it passes. Yep, we pass. So that's a fairly easy one. Okay, so we gonna write a little bit note here. Fairly easy. We use DFS to find the node of interest, which is the node at d-1 depth. From there, we can create a new node and attach the original left and right subtree root to the left and right branch of the new nodes. We also have to set up a special case for d equals 1. on, and our runtime is 52 milliseconds, which give us 82% ranking. Yep, that is that. We have a solution here. Take a look. It's not complex. It's an easy question. Oh, it's labeled as a medium. That's an easy one. Using recursion. Okay. One is this. Yeah, insert one. Then left to new, left to left, right. Else, and call it. Yeah, that's the same one. Using stack. Oh no. This is the same. You're just writing it in the stack. No, I'm not doing this. BFS. Okay, we can do BFS. Oh my dear lord, look at the BFS. Horrendous. We can think about DFS. Oh, man. When you have a like as elegant as a DFS, you kind of don't want to go anywhere else, huh? Yeah, I think DFS is the easiest. I mean, ours is even shorter than this. This one can be simplified. Yeah, this one can be simplified. Anyway, BFS. So what do? You can easily find the level that you want. We also only want to go D-1. So we find the D-1 level, and everyone comes out from the D-1 level, and you do this trick. Yeah, it should be easy. Why is it so long? No. It's the same. So you find it. It's a double Q. Yeah, it's a double Q method, and you find the depth. And come out. So the current Q is our desired depth, and then in here you do this. Yep, exactly. So BFS. Nah, 2Qs is just for 2Qs is for simplicity, not simplicity, like uniformity. That is how, in general, Qs are BFS is used. If not, how do you do with just you iterate the Q size, and then what? And then Q dot pop dot front, and then pop, and then you push to the end. Oh, okay. Oh yeah. Maybe we should use this one. Oh. Yep. I actually want to write BFS. Yeah, this is an easy question. Let's do a BFS. Yeah, I saw that. How short are you talking about? Yeah, that's about right. Yeah, DFS. Anyway, I think we want to try a BFS. Just get us more comfortable writing DFS solution. I agree with that. Did I upvote on that one? I agree that for a better BFS, we shall just use one Q. Yep, and then Q for Python, we're gonna import collections, import deck. Right, we're gonna do a deck and only one Q. Yeah, instead of two Qs, one Q shall be sufficient. Anyway, this is definitely what we have to do, and then we're gonna say a Q equals a deck, And then the deck, we're going to put the node into it. So I'm going to put the root into it. So we're going to also do the depths, right? We're going to do the depths. I like to call it level. So level is 1. So I'm going to say while level is smaller than d minus 1, so we want the level to be d minus 1. So while the level is smaller than d minus 1, then we're going to consume. Right? We're going to say for I in range len q, right? The current len. Oh, but it will change. No, it shouldn't. It shouldn't. When we call that, it already computes. Let's try it. This is something because the queue we'll be changing the queue, right? We'll be changing the queue, but I'm not sure. I think this one's already set in stone, so it shouldn't matter. So I'm gonna traverse through it, and we say node equals queue dot pop left, right? Want to pop it, and then we're gonna say if node dot left, then queue dot append node dot left. If node dot right, queue dot append node dot right, right? So we do that until we finish it. Once we finish it, level gonna plus equal 1, and once we done, now our queue holds, so we can just say while queue node equals queue dot pop left, and then we do this trick. We do this trick here, and we done. Now we just return root. Yep, let's give this a shot. Put it here. Run the code. Take a look. Solution is not defined because I said solution 2. We caught it this time. You have to always remember run local before submitting. So it's correct. Yes, I think it's correct. Yep, same runtime. So yeah, this is I think this is the best way. BFS. Plus, I think this is actually the best way to do BFS with one queue and efficient in memory. Notice that we use len q to determine how, I think I spelled it wrong, to determine how many nodes are in a level. This way we can keep pushing new nodes into the queue while still being able to stop once a level is completely traversed. This is also ON, and we run at the exact same runtime. Of course, the percentage is the same. All right, that's it. That's it for today. 2 solutions, BFS and DFS. Honestly, they're about the same. They're the same because we use the same trick here, right? And then the BFS, you have to figure out the data structure, but the way I see it, this is the best way to do a BFS using only one queue. It's efficient because we keep popping, keep adding, so it doesn't grow infinitely. the way that I used to do in the past, it does grow infinitely. And we also avoid using 2 queues, which, it's not elegant. This is more elegant. All right, that'll be it. I'll see you guys tomorrow. Adios.